And we did this a little bit in pre-calc, college algebra. I would give you a graph and I would ask you to write the intervals where it was continuous. And we used a pretty informal definition then. We said, well, it's continuous if I can draw this without picking up my pencil. Right? So intuitively we kind of know something like this would be continuous, but something like that would not, because I have to pick up my pencil. So we're talking about when graphs are continuous, because a lot of the calculus concepts only apply to continuous functions or places where the graph is continuous. So we need to be able to identify them. So with our limits, we have found sometimes we are able to just plug in the x we're approaching. You know, if I said the limit as x approaches 1 of 2x plus 3. That's a polynomial, so we said we could just plug it in and we get 5. But if I gave you the limit as x approaches 1 of x squared minus 1 over x minus 1, can you just plug it in there? No, because it gave us 0 on the bottom. Well, there's a little more to it than that. The reason this one doesn't exist at 1, I can't just plug it in at the beginning, is because it's not continuous there. The graph itself has a discontinuity. So if the graph is continuous, you can just plug in your x value. If it is not continuous, that's the problems where we were trying to factor and reduce, or multiply by a conjugate, or multiply things out. So those were the problems that had more work involved. There are 3 things that it takes for a function to be continuous, and you need to know these. All right. First of all, the function has to exist. All right. When I plug in that number, I can't get something divided by 0. It has to be defined. The limit has to exist, and the 2 things have to be equal. So the function exists, the limit exists, and they are equal to one another. We talked about this already. It's continuous if there's no break in it, if we can draw without picking up our pencil. Any place where you do have to pick up your pencil or there's a break in the graph, we call that a discontinuity, a break in our continuity. So if I ask you, where is this graph discontinuous and why? So first, can you tell me for what x values is this graph discontinuous? If you were drawing this, where do you have to pick up your pencil? When x is 3. What else? When x is 5. And one more, when x is 1. The reason, so we're calc kids now, we can't just say you pick up your pencil. We have to give a better definition. We have 3 rules of continuity. The function has to exist, the limit has to exist, and they have to be the same. When x is 3, does the function exist? Is there a place when the x is 3? Yes. Does the limit exist at 3? No, because when you're coming in from the left, I'm down here. When I'm coming in from the right, it's up here. So the reason...
Nicole Carey, please come to the gymnasium. Nicole Carey, please come to the gymnasium.
Is that the limit doesn't exist right there. That's the rule it breaks. When I plug in 5, does the function exist at 5? Yeah. Does the limit exist at 5 when I'm coming in from the left and right? Do they match up? Okay, the third rule says the function has to equal the limit. That's the one it breaks. So the limit is not equal to f of 5, or you could say the limit doesn't equal the function. You don't have to use all the correct notation. You can just tell me in words, that's fine as well. The last one, when x is 1, does the function exist when x is 1? No, I have an open circle in my graph. So the reason is f of 1 does not exist. So this graph showed us the 3 scenarios that cause it to be discontinuous, which rule you might be breaking. So on any of these problems, if I ask you to tell me why something isn't continuous, you have to tell me which of the 3 rules it broke. All right, graph of f of x equals 1 over x minus 2. Okay, you could use a calculator. We could also probably get a graph by hand, couldn't we? Where's my vertical asymptote going to be at? 2. Remember that from last year? The bottom 0, you get an asymptote. If you wanted to plug in some points, when x is 1, you get out negative 1. When x is 0, we get negative 1/2. When x is negative 1, we're getting negative 1/3. Section's kind of looking like that. If I put in a 3, I get 1. 4 is giving me a half. This section looks like this. Or we could use a calculator for a class example to get a graph. So, where is this graph discontinuous? Which we kind of knew just from the function itself. That's the one that doesn't exist. What rule does it break? Or maybe I should even say rules. Does the function exist? No. F of 2 does not exist. Does the limit exist? No. So this one actually broke all the rules. The function doesn't exist and the limit doesn't exist. Now, on those problems, if it breaks multiple rules, you just have to tell me one. You don't have to tell me if it has multiple issues. One of those would be sufficient. Let's look at another one. Graph this. If x is 0, we get out 1. If x is 1, anytime you put in something bigger than 0, you're getting out 1. If x is 2, we're still getting out 1. This one you would have to start with 0, and it gives you negative 1. If I put in negative 1, I get out negative 1. Put in negative 2, I get out negative 2. You guys understand how I drew that graph? Really just did a T-chart, but I talked through it instead of writing it out. Okay, so where is this discontinuous? What rule does it break? The function exists at 0. When I plug in 0, I do get an answer, but my limit doesn't exist. The left and right hands don't match it. Let's take a look at each of these and see if we can figure them out. I want to know where each of these would be discontinuous. Can you look at the equation and tell me where A would be discontinuous? 2. Why? So my reason is f of 2 does not exist. I can't plug a 2 in. So fractions, we're looking, the obvious is when the bottom is 0. That's when it's discontinuous. B. What do you think on that one? Why? Okay. If you remember, if you used a calculator or plugged in points, 1 over x squared looks like this. Okay, so the limit as we approach 0 is infinity. 1, if x equals 0, is just a single point. So does f of 0 exist? Does my limit exist? It's going to infinity, so it does. Both sides are going up. But my reason is the limit does not equal the function. Yeah, because it's a 1 over x squared. If it was 1 over x, they would be going opposite ways and the limit wouldn't exist. All right. Let's see. Where do you think that one might not exist? At 2. Why? Okay, we have 2 different pieces. One when x equals 2 and one when x does not equal 2. We could, if we needed to, graph this a little bit. The top would factor into x minus 2, x plus 1 over x minus 2. What happens to those x minus 2's? So that just gives us x plus 1. We're on that piece if x is not equal to. So when x is 2, that would have to be an open circle. 2, 3. And then everything else we could plug in. So if I put in 1, I get 2. 0, 1. So that top piece is just a line with the whole limit. 1 when x equals 2 is a separate point. So we can see it's not continuous when x is 2. Does my limit exist? Yeah. Does my function exist? Are they equal? So graphs can be helpful if you can't tell from the equation itself. Alright, last one. What does that symbol mean? Greatest integer function. Remember that one? It's like your step function. Like this. Where is that one discontinuous? Okay, does the function exist at the integer values? Yeah, does the limit exist? No. All right. So we had several different types of discontinuities here. There are 3 actual types. We can categorize them. There's removable, infinite, and jump. Okay, A and C are what we call removable discontinuities. Part A, we didn't graph it then, but it was just this line with the open circle in it. It's removable if it's just an open circle, because it could be fixed if by filling in the circle. Okay, I removed that one point, I could fix it by putting that one back. So that's a removable discontinuity. B is what we call an infinite discontinuity, because I have a vertical asymptote. It's going to infinity. So if it's going to either infinity or negative infinity, that's an infinite discontinuity. D is what's called a jump discontinuity. I'm at that piece, and then I physically jump to the next. So those are the 3 different types that we might see. Removable is an open circle. Infinite is a vertical asymptote. Jump is when you're stepping from one to another. And we could have functions that are continuous, like I could ask from the left or the right. So that is still an option. Just like with limits, we can have a limit from the left or a limit from the right, so that could happen. What if I ask you this question? Where would this function be continuous? Everywhere. This is a polynomial, right? We know polynomials are always nice smooth curves. There's no break in that curve at all. So it's continuous from negative infinity to positive infinity. So polynomials are always continuous. What about this one? What if I'm dividing polynomials? Can you look at the function itself, not the graph, and tell me where it would be discontinuity, or where it would have a discontinuity? And the reason is in a fraction, we know the bottom can't be 0. So x can't be 5/3. So it's continuous everywhere else, from negative infinity to 5/3, and from 5/3 to infinity. Reason, function doesn't exist there. Can you tell me what type of discontinuity this would be? So it could either be removable if you factored the top and it canceled out, that puts a hole in the graph, or if it doesn't cancel with the top, it would be infinite because you would have a vertical asymptote there. The top actually doesn't factor on this one, so it is an infinite discontinuity. All right, why don't you guys take a look at the next, well, let's do this one together and then I'll have you guys try one. If I said x cubed over x squared plus 2x plus 5. If I want to know where that's continuous, with a fraction, what am I worried about? Okay. Same thing, multiply to 5 and add to 2? No. If I did quadratic formula, opposite would be plus or minus the square root squared minus 4ac all over 2a. Getting 4 minus 20, which is a negative 16. What happens if you're getting a negative under your radical? Imaginary. Is that going to impact our graph then? No. So where would this one be continuous? Everywhere. Because the only place it wouldn't is imaginary. All right, you guys try this one. Figure out where it is continuous. So in a fraction, the bottom can't be 0. Factors of x plus 2x minus 2. So x cannot be negative 2 or 2. So it's continuous everywhere else. So from negative infinity to negative 2, between negative 2 and 2, and bigger than 2. Any questions there? Okay, we are going to switch gears. I want you to take a look at this handout I just gave you. And we are going to work through some of these together. So we're really focusing on what makes things continuous or not. We know with fractions, we are worried about the place where the denominator is 0. When I look at this first one, if you have a piecewise function, where do you think the issue might be? The 1. When you have a piecewise, when you jump from one piece to the next, is where you could potentially have an issue. Now, is it possible to have a piecewise function where the two pieces line up? Yes. So what we need to do, that's the only place where it might not be continuous. Let's check. I know on this one, if I put in 1, I get out 0. What happens if I put in 1 on the second piece? So, do they match up? No. So this one is continuous everywhere else. So from -infinity to 1 and 1 to infinity. It's not continuous at the 1 because I am jumping from one piece to the next on my graph when I do that. If I look at the second one, we have a fraction. Is the bottom ever 0? So where would this be continuous? Everywhere. Okay, third one. What do we have to worry about? Denominator. I know x squared minus 3x cannot be 0. So we can factor out an x, so x cannot be what? 0 and 3. So it's continuous everywhere else, from -infinity to 0, between 0 and 3, bigger than 3. Last one. Where am I worried that it might be an issue? At 1. I know the second piece, this is the point 1, -2. So if the first piece is also 1, -2, I'm good. It's continuous. If it's anything else, it's not. So if we put 1 into the first one, I get 2. So is this one continuous there? No. So it's continuous from -infinity to 1 and 1 to infinity. Questions on those? All right, so the next set, we're going to do the same thing. We're going to decide if it's continuous, where do I have a problem, but then I want to classify it. So remember, when I say classify, we are talking about our 3 types of discontinuities. Removable is a hole in the graph. So that happens if you have something in a fraction that cancels, that makes a hole, or if you have a piecewise function where your conditions are not equals and equals. Because this first one, you would have a line, except when you plug in 0, it would be an open circle, and the second one gives you a point. So the 2 places you can get a removable discontinuity are when your fractions, you have a factor that cancels, or if it's a piecewise function where one condition is not equal and the other is equal. What's the next type of discontinuity? Infinite. Okay, infinite, you're looking for a vertical asymptote. Something like this. It doesn't cancel out, so I have a vertical asymptote when x is 3. So that would be an infinite discontinuity. What is the third type? Okay, so we saw a jump on our greatest integer function. The other place you're going to see it is piecewise functions. Where one piece is like greater than and the other is less than, assuming the 2 pieces don't match up, because we know it's possible they match up, in which case there is no discontinuity. So we can predict the type just by looking at our equations. if I look at number 5, it's either, fractions mean it'll either be infinite or removable. What do I need to do to check? Factor the top. Since the x plus 2's would cancel, we know it is discontinuous when x is negative 2. And then what type would we call that? Removable. Because it will just create a hole in my graph. All right. If I look at number 6, what type might this be? Yeah. So when I look at my conditions, removable, we have to have a not equal and an equal. That's not what we have. So less than, greater than, that tells me it's a jump. But what should I verify first? Make sure they don't match up. The first one is the 0.10. Second one, if I put in a 1, we get negative 1/2 plus 3/2, which is 1. So that's 1, 1. So they don't match. So this is discontinuous when x is 1, and it would be a jump because you would physically jump from one piece to the next. Why don't you guys try a couple? All right, so if we look at number 7, you can factor the bottom, but does anything cancel out? No, so it's discontinuous at both x equals negative 3 and positive 1. And what are both of those? Infinite. Now, if one of them canceled and the other didn't, they would have still been both discontinuities, but one would be infinite and one would be removable. So that can happen. When I look at number 8, this is negative 2, 0. First, we need to see if the pieces match up. So if I put a negative 2 into the top piece, we get 4 minus 12 plus 9, and that gives me 1. So they don't match up, so it's a discontinuity. What type would it be? When we have an equal and a not equal, removable. The not equal is just a hole on the graph, so holes are always removable. When I look at number 9, you can factor an x out of the bottom. Nothing cancels, so it's discontinuous at both x equals 0 and negative 3. Since neither canceled, they are both infinite.
So the 0 can't cancel?
Oh, sorry. I just wasn't paying attention, was I? Negative 3 is infinite. What would 0 be? Removable. All right, last one. Where is it discontinuous? What type? Because it would be a vertical asymptote.
It's almost like if it can be like removed from the situation, it's like infinite equation, it's removable.
Yes. And removable ones can always be fixed if we just like added another point on our graph. All right. How are those? Is that okay? Let's go ahead. We'll do this back, and that will be where we stop today. Okay. So I want to decide if they are continuous or not. Now, we've been talking about this, so we should be able to kind of tell what type of discontinuity might I be looking at here. jump when you jump from one piece to the next. But we can always confirm this by a graph, right? So I just wanted to practice that graphing. Piecewise function is always good to remember how to graph. You can write out a t-chart if you need to, or at least do it in your head. You have to put -3 into the first piece. But since it was open, or not equal to, it'd be open. If we put in -3, I would get -9 plus 12 minus 4. So -1. So -3, -1 is open. Then we need things less than that. So if I put in -4, -16 plus 16 minus 4 would be -4. If you did -5, you get -25 plus 20 minus 4, which is -9. Okay, so we can see this piece looks like that. The other piece, what do you have to plug in to start? But it would be closed because it was equal to. So -6 plus 1 is -5. If I put in -2, -4 plus 1 is -3. If I put in -1, -2 plus 1 is -1. So this kind of confirms what we've been talking about, just gave us that visual. So it's discontinuous at -3. What type was it? Jump, just like we predicted. Number 12, what kind of discontinuity might this one be? Removable, because we have an equal and a not equal. In terms of graphing, you still put the 3 in the first piece, but it would be open. And then you can put in anything else, so things bigger or smaller. So if you put in a 3, you get -1.5. If we put in a 2, we get -1. If I put in a 4, we get -2. So we have this line with an open circle on it. 2, when x equals 3, is just a point. When the x is 3, the y is 2. So this is discontinuous when x is 3, and it's removable. We have